Okay. Yeah. Good afternoon, everyone. Welcome to the last session of this day. So I'm profusely excited to take an opportunity to introduce the last speaker of the day, Dr. Borbala Puniaji. So yeah, thank you, Bori, for accepting our invitation. So Borbala Puniaji, in short, we call her, we call her Bori. So she was born in Budapest, Hungary. She received a MSc degree in electrical and computer engineering from the Kazimierz Peter Catholic University in 2009. In the same year, she joined the Studios Department of Electrical Engineering at Cave level, where she worked in close collaboration with the Laboratory for Epilepsy Research, and she obtained her PhD in 2014. She continued working in studios as a postdoctoral researcher on the ERC Advanced Grant Biotensors, and she served as a research lead on the IMEC Icon project CGIT. Between February and May 2016, he was a visiting researcher at the University of Oxford, and in May 2017, he visited the I'm sorry if I pronounced it wrongly, Albrecht, yeah, Christian Albrecht University of Kiel.
Yeah.
In 2018, he was awarded one of the TED Technology Fellowship for Outstanding Female Academic Researchers. In October 2018, she joined the Circuits and Systems Group at TU Delft as an assistant professor. Her research interests include biomedical signal processing and machine learning for biomedical pattern recognition. More specifically, she is interested in multimodal signal processing and fusion, blind source separation, tensor decomposition, and wearable signal processing to better understand healthy and pathological physiology. In particular, brain activity in epilepsy. And also, I would like to say one thing that I was very fortunate that I was part of that ERC grant biotensors. I'm really thankful to Sabine who gave a very nice presentation day for yesterday. I'm very fortunate that I met all those people there in Belgium. Yeah, so without further delaying, I would like to request Bori to present her thoughts for us, what she has for us today. Yes, over to you, Bori.
Yeah, thank you very much for the nice introduction and for this invitation. I'm very glad to speak to you here, and so in the next I think a bit more than an hour, I'm going to talk about the power of tensor-based AI tools in functional neuroimaging, and most of the examples that I will show you will be about epilepsy, but in the very end I will also show you a little bit outside of this field if there is time. Especially in the beginning, I would like it to be a little bit interactive, because I think you have heard about tensors by now, at least from Siva's presentation earlier today, was it? But still, I would like to go over some of the basics to make sure that you know what I mean by certain terms. Also, to make sure that some of these basic terms are clear for everyone, because if you want to go and read application-based papers, being familiar with these basics will be, I think, a lot of help. So yes. Here is a short outline of my talk. So first I will talk a bit about motivation. So first of all, what are tensors and why do we want to use tensors in AI or in machine learning? And this will lead to defining the goal of my lecture. Then in the second part, as I told you already, I'm going to talk a little bit about the basics of multilinear algebra or tensor algebra. I will present you the matrix SVD and how this matrix SVD generalizes to tensors. And I will discuss two tensor decompositions. And finally, I will show you some applications where especially the first decomposition, CPD, is used, but I will also go into a little bit more complex models towards the end. Okay, let's see. You have seen this, but let me just repeat what a tensor is. A scalar, of course, it's a single number. So if at this moment I would put an electrode here on my drain, on my head, and I would measure the signal at a certain time at a certain location, that's one value, that's a scalar value. Now, of course, this is not very interesting. You want to monitor brain activity over time. So you would stack single measured values at different times into a vector T. Okay, but in EEG, but in many other applications, we of course measure not only at one location but at several spatial locations. And then if I stack the measured signals, so these vectors, which are measured at different spatial locations, I will stack these into different columns. So right after each other, then I get a measurement matrix. So this is pretty clear until now, but sometimes you want to go even further and add more dimensions to the data. Sometimes the data is inherently multidimensional, and then we need a 3D structure. So a tensor is nothing more than a third dimensional or higher dimensional generalization of a matrix, where we pick matrices and then we stack matrices behind each other, and that will grow into a tensor. Now, can you name some real-life tensor data? So can you think of some data which comes in 3 dimensions or more? You can use the chat if you would like to answer my question. Or you can turn on the microphone, of course.
Video frames?
Yes. Very good example. Because there, of course, we have the X dimension, the Y dimension, and then we have basically images over time. So that's inherently a tensor. Very nice. In fact, already a color image might be represented as a tensor, because a color image will have 3 color channels, right? Red, green, and blue. And well, then basically you have 1 image per color channel, right? Yeah. So an image, as I said, a video. Actually, if you then extend the video, an RGB image into video, then that's already a 4th order tensor. Another, well, very, I think, basic example is some weather data, right? You want to monitor the weather, how it changes hour by hour during the day, but it also has a cyclicity over days. Each evening the temperature goes down, in the day it warms up. And you want to monitor the weather in different locations, because perhaps you work in a city and live in another city, like me. So I want to monitor how the weather changes per days and per hours, and then I have to stack my data into tensors. So the 3 variables, or the 3 factors along which the data can change, define the 3 dimensions of my matrix. Right. There are also some more scientific or more, less everyday type of data which come in as tensors. I just wanted to mention a few hot topics which involve tensors. For example, if you want to do some machine learning over a multi-layer or time-evolving networks, what could a time-evolving network be, or a multi-layer network? Let's see the example B. So what you see here is a network of cities over Europe, and two cities are connected with each other if there is a direct airline connection between them. Now you can draw then a network of European cities regarding Ryanair, which is one low-cost airline, but you might want to draw this using the network of Lufthansa. So each airline will give you a different network. And well, why is this a tensor? Because a network or a graph can be represented as a matrix, an adjacency matrix, where each element in the matrix tells us whether there is a connection between CTI and CTJ. Okay, so then you have these adjacency matrices which describe one network, and then you have to stack the networks of the different airlines behind each other. And then you have suddenly a multi-layer network or a tensor. So, well, such networks come every day. You can think of social networks. You can also think of brain networks. A lot of research is being done on multi-layer networks. A complete different example, and this is also, it's a new research topic that I'm working on, and it concerns 3D ultrasound of the prostate. And we are trying to detect prostate cancer based on the ultrasound recordings. So I said it's a 3D ultrasound. So I'm measuring the whole volume of the prostate. So I have data in X, Y, and Z dimension, but it also has a time dimension because we are measuring basically how a certain contrast material or bubbles flow through the blood vessels. And for this, we need to monitor this 3D volume over time. And finally, an example which I will talk more during this lecture, and well, I said this already, a multi-channel EEG, so measurements over the head, that's already a matrix. And if you want to compare the measurements of different seizures or different patients, then you might want to stack the measurement matrices behind each other, and then you have
Hello, sir. Hello, sir.
third order tensor. Yes?
Yes, sir. Okay, sir.
What do you continue?
So how can we deal with tensor data, or what is the problem? The problem is that traditional machine learning methods or AI tools or traditional signal processing work on matrix data. So traditionally, what people have done is that they unfolded a higher order data into a matrix or even into a vector. So for example, here is the very famous Lena. And if you want to, if people wanted to work on this traditionally, what they would do is they would take the first row of pixels and store it somewhere, then take the second row of pixels and store it right next to the first row. So basically they are unfolding this matrix into one long vector. And like this, you can handle this data with traditional methods. The only problem is that obviously you're losing information because you're losing the information that pixel here, so the edge of the hat, is actually near this other pixel, right? So if you unfold, then this neighborhood information is lost. The structural information of the matrix is lost. The same with the tensor. If you're unfolding it, well, it's possible to make it to a matrix. You preserve the values, but you lose the information that these values actually belong together. So here is an overview image of different machine learning methods or classes of methods. You can see there is supervised learning, unsupervised learning, and within each paradigm there are also different tasks. Oh, okay. Now I will do the slideshow because you're not seeing my nice animations. I'm sorry. So there is matrices occur in machine learning everywhere. Really, I cannot name a single machine learning method which does not use matrix data. So for example, in regression analysis, there is the so-called design matrix, which it connects. It tries to connect my measurements with possible underlying independent variables or factors which might underlie the data. In superfactor machines, there is a kernel matrix which tells us the similarity, basically, between two training points. In independent component analysis, there is a mixing matrix which connects, which are basically weights which connect our observations with the strength of different underlying sources. Then in hierarchical clustering, you start from a covariance matrix of the data. So basically, matrices are everywhere. Now, what happens if your data is not coming in a form of a vector or a matrix? What can you do? You either unfold, or you have to extend all these methods to tensor methods. So there exists tensor regression already. There exist support tensor machines. But I'm not going to talk about these. I will talk about a blind source separation. So that's related a bit to independent component analysis or factor analysis. So we are going to see how you can do blind source separation of tensor data. And we will, that's basically CPD or canonical poorly decomposition. Or in many literature, especially psychometrics, they call it parafact, but it's the same thing. And you can also extend principal component analysis. So when your data comes again in a form of if each observation or data point is in fact a matrix, then you might want to use a multilinear PCA or a multilinear singular value decomposition. So let's see I would like to show you some intriguing examples, what tensors can achieve. Does anyone have any idea what is on this image? So this is obviously a corrupted image. During transmission, a lot of information is lost. So all the black pixels you see, they are lost. But can anyone guess what was on the original image? Any guess? Now I don't see the chat, so please guess by talking to the microphone. It's just a game, you cannot say anything wrong. Well, I'm not surprised that there are no guesses because I would have no idea.
Even I can't say.
Yes?
Yeah, I cannot guess what is it.
Okay.
What is there.
No. It's very, very difficult. But let's see if an algorithm, a tensor-based algorithm, could guess. So this is what a tensor-based algorithm reconstructs from this image. So it looks like that these are some farmhouses. And let's see the original image. This was the original image. So I think this is really remarkable that we have no idea. Our eyes have really no clue what we are seeing, but a tensor-based AI tool can reconstruct this image pretty well. Then again, an example from a complete different field, and I will talk about this much more. If we have an epileptic seizure recorded in the EEG, what we want to be able to tell based on this image is where the seizure originates from. So we have a multi-channel EEG. Here are the different channels. And the question is, on which channels is the EEG the strongest? Because we can assume that where it is the strongest, that's closest to the origin or to the focus of the seizure. And we will see that, well, we also have the ground truth from an imaging modality. So this is not based on EEG, but a SPECT image. But the question is, I mean, it is very expensive and impractical to obtain these images. So the question is, could we get the same information out of the EEG itself? And the answer is yes, although I have to acknowledge that the spatial resolution is not as good as in the image, but by a smart tensor decomposition, we are able to to get these relative weights over the EEG channels. And so the largest weights, which are indicated in red, they actually coincide with what we have seen on the SPECT image. Later on, I will explain in detail how this works. So the goal of my lecture will be to first of all explain you the basic principles behind CPD and MLSVD, and then finally give you examples of how these rank 1 decompositions can be of use, and I'll also extend it a little bit to slightly more complex decompositions. Right. Are there any questions about it so far, or any comments that you want to add? I'll get a
excuse me, ma'am.
Yes.
What type of noise that is being added there, whether it is some kind of a Gaussian noise or a mixture of other type of noises, so that the complete information is lost in that image?
It's not noise which was added. The complete information was lost. So I think either, well, I took it from a paper of a colleague. Either those pixels were given a value 0, or maybe they were given the value none, so not a number. It was just basically lost.
Thank you.
Okay. Yes.
Yeah, but from that noisy image or corrupted image, people try to reconstruct the image using tensor decomposition, right?
Yes. Yes. Basically, assuming that that this image is somehow low rank, and imposing this this constraint or this assumption. Yeah, just from those few voxels, you can construct back an image. And why it works? Because real life data and real life images are usually of low rank. There are many correlations in the data, both along the rows and across the columns. And that's why it's very important to keep the original shape and not vectorize. Once you vectorize, then a lot of this information is lost. And basically, when you vectorize, then you would lose the information across the columns, because you lose the basic information that this column was, or this pixel was close to that pixel.
Okay, so is it kind of missing value retrieval? Or?
Yes, exactly.
Okay. That's a nice, yeah, you carry on here.
Yeah. In the end of the last slide, I put the references to all these examples and images, so you can consult the original papers for the details. And I will give you a link to my presentation. Okay. How are we with time? Well, very quickly about some of the basics. So a lot of very, very important concept in signal processing and in machine learning is the rank of a matrix. So if we want to go from a matrix to tensor, then we also need to generalize the notion of the rank. Okay, and that's what I'm going to do during the next slides. But before, let's just clarify some terms. So the columns, the rows, or the tubes of a tensor are called fibers or n-mode vectors. So these are the vectors which constitute a tensor. And of course, this can be generalized to higher dimensions, but it's not possible to draw these. But anyway, I talked about unfolding. So how to unfold the matrix, that's very clear. You take one column, then you take the next, you stack it below. The same thing you can do with a tensor, and then you make it into a long matrix by taking slices of the tensor and putting the slices next to each other instead of behind each other. So then you get a long matrix, or a tall matrix if you do it along the other dimension. There are two very important products. The Kronecker product, that's a little bit more known. So basically the Kronecker product of two matrices, that will be a larger matrix. So if the original was I1 times I2, the second one was I3 times I4, then this is becoming a matrix of I1, I3. So that's the number of rows, and the number of columns will be I2, I4. Okay, so we are combining, yeah, like that. And the elements are defined like this. So each, the matrix, it's basically a block matrix where each block is a scaled version of the second matrix. Okay, so and the scaling is defined, the scaling of B is defined by the elements of A. Now a Khatri-Rao product is basically a column-wise Kronecker product. So if I have two matrices, then what I do is I take columns of the corresponding columns of the matrix. Here it's very important that the two matrices have to be of the same size. So then I take the first column of the first matrix, the first column of the second matrix, I take their Kronecker product, and yeah, that's my first column. And well, this might seem, yeah, not so easy to understand. I think there is another and better way to understand the Khatri-Rao product. Is what I do is I take the first vector and the second vector of the second matrix. I take their outer product that forms a rank 1 matrix. And if I vectorize this matrix, that will be the first column of the product. So again, I have to take the outer product of corresponding columns from each matrix. That gives me a rank 1 matrix a rank 1 matrix for each pair. And if I vectorize this, then yeah, then that will be each column of my matrix. So this corresponds to this column, the second term corresponds to the second column, and so on. And this is important because it will come back later when we talk about CPD. So I suggest if you want to get deeper into tensors, then once you make an example, you try to write down the example of two simple matrices and how the Khatri-Rao product looks like, and it will become much more clear. Then you can also take an n-mode product of a tensor and a matrix. And here's the definition. I think the definition is very difficult to see or understand, but let me maybe make a drawing for you, which will make it much simpler. One moment. Okay, my iPad disconnected. I'm sorry. I wanted to draw this for you, but I will try to explain it in words. So taking an n-mode product of a tensor X and the matrix U is nothing more than, for example, taking the first slice for the first matrix within this tensor, multiplying it with U. That will give you a new matrix with a different size. And then you keep that matrix. Then you go to the second slice in X. Maybe let me go back to, yes, let me explain it like this. So first you would take this matrix here, the first slice, you multiply it with your matrix, and that gives you a new matrix. Yes, then you save that matrix. Then you take the second slice, again, multiply it with the matrix U. Again, you get a new matrix. And you organize these back into a tensor in a similar way. So you will have basically the result will be a matrix or a tensor, which has a different size, but they are organized in the same way. So the first slice of the new tensor will be the multiplication of the first slice of the old tensor with the matrix. Okay, so I think this looks very difficult, but in fact, is just doing normal matrix operations and organizing the results the same way as the original tensor was organized. Yes. Now, very important notion is the rank of a matrix. Now, you might remember from linear algebra that you can define a column rank of the matrix, which is the number of linearly independent columns of the matrix, and it's denoted by RC. The row rank is similarly the number of linearly independent rows, and it's called an RR. Now, another way to define the rank is in terms of the minimal number of rank 1 matrices that yield T in the linear combination. So in other words, how many rank 1 matrices do I need to add up to get to my original matrix? And this kind of rank is called rank, it's just denoted by R. Now for matrices, we have all learned this in linear algebra, but I can imagine it was a long time ago, but the column rank and the row rank is exactly the same, and it's equal also to this other notion of the rank. So let me give you an example. This is a simple rank 1 matrix. How do I get a rank 1 matrix? I take the outer product of a vector and another vector. And this is the result of the outer product. And you can see that basically each column is just a scaled version of the other. So to get this, I just have to multiply this column with 3. Also the rows, if I check the rows, this second row is just the same as the first row, but scaled by a scalar of 3. So again, I mean, so this is the rank 1 matrix, and you can also say that, the number of linearly independent rows and columns is 1. Because I just showed you that they are the scaled versions of each other, so they are linearly independent. Now, what is the rank of a tensor? So if I want to generalize this previous notion to a tensor, so again, we have to count how many linearly independent columns or rows it has. But let's see first how many linearly independent columns we have. So let's see, this the first column is a 0, 1. Then the second is 0, 1. So those are not linearly independent. I'm still at 1. Then I have 1, 0. That's linearly independent from 0, 1. So that's 2. And 1, 0, that's the same as previous. So it has 2 linearly independent columns. And you can do the same for the other dimensions. So let's see for the rows. 1, 1, that's the same. I mean, that's 1. Then I have 1, 1 again. That's still the same thing. I have 0, 0, but that's not linearly independent from 1, 1, because I just I multiply it with 0 and I get the same thing. And then I have 0, 0. So the number of linearly independent rows is 1. So very interesting. This notion of the rank, for this notion, you can have different ranks along the different dimensions. So this is very different as for the matrices. It's important to remember. Consequently, also the other notion of the rank will be different. What was the other notion? How many rank 1 matrices do I need to add together to get my matrix? It will definitely be different. So, but we need to generalize both views on the rank, the notion of linearly independent rows and columns, and the notion of number of rank 1 constituents. And we will use SVD to generalize these. So I hope you all remember singular value decomposition. You can do this for any matrix, and you can write any matrix down as the multiplication of 3 matrices, where the first matrix and the third matrix, so U1, they are orthogonal matrices, and they form the basis for the column and the row space of a matrix. And you have this diagonal matrix. So it has zeros everywhere except on the diagonal. And these elements are called the singular values. They are non-negative and they are ordered by definition. So these are the largest singular values and those are the smallest one. And in fact, the number of non-zero singular values tells you the rank of the matrix. Remember also, if you have a noisy data, you might have all singular values non-zero, but these last ones are usually quite small. So you can find a threshold where you truncate your matrix and you make everything else equal to zero. You can reconstruct, and basically you have denoised your matrix. So if you truncate SVD, this is really a basic tool in signal processing, SVD truncation, it will always be the best rank R approximation of your original matrix in a least square sense. Then the other way of looking at SVD is really just the same thing. What do I do here? Compared to the previous slide, I take the columns of these matrices and the rows of this matrix, and I take their outer product and I scale them with the singular values. So it's really the same thing as before, just a different representation of the same operations. But basically, this will tell me that to write down this matrix, I need R number of rank 1 matrices added together. Okay. Now, now I will show you how to generalize this, this first view on SVD. Oops, I lost it. Sorry. So how to generalize this one? That's the multilinear singular value decomposition, and this is how it looks like. So you have a tensor that you want to write down as the multiplication of a so-called core tensor and factor matrices. And for this, I use the N-mode product, which I explained you before. But basically, it's true that these matrices are orthogonal. Although this core tensor is in general not diagonal, but there is some ordering. So the larger elements in general are here in the corner. Okay. In some cases, similar decompositions exist, and they are called Tucker decompositions. So this is a Tucker with orthogonality constraint. Now the other way of generalizing SVD is okay, sorry, but just one more notion on this. So to compute it, it's very easy. You can just compute it by taking an SVD of the unfolding of the original tensor. And it has very important applications. So for example, low multilinear rank approximation. So again, if you want to, sorry, I'm messing up the order of the slides. Yeah, so if you want to denoise a tensor, then again, you can just truncate the core tensor or truncate the columns, the last columns of the factor matrices you ignore, and you reconstruct, then you will have a denoised or approximated tensor. So it's used for denoising. It can be used for feature extraction. You can use it for compression and signal enhancement. But I will not talk too much about this in this talk. More interesting for us is the other generalization of the tensor rank. And I'm depicting it here. So this is your tensor, and then you want to write it down as the sum of rank 1 tensors. And what is a rank 1 tensor? Is an outer product of these column vectors, these vectors. Right. So, well, I think I just show you again how the SVD looked like. It's really just a very straightforward generalization because I add one more vector to these outer products. And in that way, I have rank 1 tensors. So you can write it as an equation like this. So outer product of vectors. And then I take a sum of R of these products. Or another way to write the same thing is this equation. Yes, where I collect the vectors from the same direction, and I put them into a factor matrix. And here comes the Catry-Rao product, which I explained you. So again, this is a matrix where I took the outer product of two vectors. That gives me a rank 1 matrix, and I vectorize the matrix. Yes, and that will be one column of this one. And if this resulting, so this Quadrant product matrix multiplied by U matrix, it gives me the matrixized version of this T. So it's an alternative way of writing the same thing. And why is this very important? I will come back to the example later. This is extremely important because if I compare tensor factorization with matrix factorization, then this matrix factorization is not unique. So if I can factorize a matrix T as a product of two matrices, or sorry, this is a bit later. I will jump a little bit further because this is very important to say now. So if I want to factorize this matrix, then I can factorize it by writing it as a multiplication of two matrices. But this is not unique because I can take any other matrix and just multiply A and multiply S with its inverse. And then I get a new factorization, which is equally good, but these are other matrices. Now for a tensor, I cannot do this. And why not? Because if I take a matrix M and multiply that with this matrix, then this structure defined by the Quadrant product, so this rank 1 structure, is lost. So if I take the multiplication here, then I don't have anymore a rank 1 matrix. Okay, so this is very important to remember. This gives a very important property of CPD, namely that it's unique. Now let me go quickly back to where I was before. Just an example of the rank 1 tensor, how it looks like. Remember, this is a matrix that I showed you before. Now, taking the outer product of this matrix with this vector will give me a tensor where the first slice is the matrix itself. Then the second slice is, the second slice is the matrix itself because it's multiplied with 1. Then this slice is this matrix multiplied element-wise by 5. And finally, this, again, is just the same matrix scaled by the factor of 2. Okay, so I have the exact same pattern over each of the slices. There is just a linear scaling difference. Okay. I think I've explained this already. So a rank 1 matrix is an outer product of 2 vectors. A rank 1 tensor is the outer product of 3 vectors. Very straightforward generalization. And I already said something about the uniqueness. There are ways to check whether the decomposition will be unique, and you can read those papers if you're interested. Yes, so there are different ways to compute the CPD, but it's mostly optimization based. For noiseless tensors, there is also an analytical solution, but in real applications, you usually have to do some optimization to fit the data. Unlike MLSVD, which can just be computed by SVD. Applications of CPD include blind source separation, factor analysis. And why is it so popular? Because the components are interpretable. And this interpretability comes from the uniqueness property. But I will explain this to you through examples. So this was a summary of part 2. So I showed you different generalizations of the rank. In the tensor case. So these generalizations give rise to 2 different decompositions. One is the MLSVD. So basically this expresses the tensor in different bases simultaneously. You can use it for compression or denoising. And the other decomposition was the CPD, the canonical polyadic decomposition, which gives you unique and interpretable factorizations. Are there any questions about this part?
Hello.
Yes, hi.
Ma'am, in mode and product, you mentioned the mode and fiber, the mode and fiber of the tensor, the product of mode and fiber with the matrix. But mode and fiber is a vector. I think it should be slice.
One moment. Are you talking about this slide?
Yes, ma'am.
Yes. So I explained it with slices, but you can. It's the same thing with the fibers. So I can take a fiber, which is one vector, and multiply the vector with the matrix, and that will give me another fiber, another vector. And I can just organize the vectors in the same order as they were in the original tensor.
But the generalization of this in MLSBD, where one tensor is mode and multiplies by many other other matrices, then I think please open the page of MLSPD.
Oops, this one.
Yes, ma'am. Suppose S is the tensor. If you multiply the mode and fiber with a matrix, and it will be the matrix. Then it's how it will be multiplied by the second matrix U2.
So if I take, let's say, so this is the core tensor, and I take this very first fiber, let's say, and I multiply that fiber with the matrix here. That will give me a new vector, not a matrix.
Yeah. Oh, sorry. Yes, vector.
Yeah. So I think if you try to write it down once, then it becomes quickly very clear. But yeah, so a multiplication of a vector and the matrix will give you a vector, and then you can organize the resulting vectors exactly the same way as they were before. So again, so this vector times this matrix will give you this vector. Similarly, like this matrix times this very last vector here will give you this vector.
Okay. Thanks.
No problem. Okay. So I acknowledge that this is a little bit difficult, but I hope if you read papers in the future, then you will remember this presentation. You can come back to it because it's recorded. So I hope it will be helpful for you in the future. I wanted to talk about it, although it might be a bit dry material. But now I will come to some examples. When we talk about functional neuroimaging, I mean neuroimaging in a very broad sense. So anything which can give us information on brain activity over time, I call that functional neuroimaging. So I'm talking about functional magnetic resonance imaging. It can be functional ultrasound, but it can also be EEG. Because in EEG, I'm recording electrical brain activity from different electrodes on the head. Now, it's true for any of these recordings that what I observe, so the time series X, so these are multiple time series. Let's say this is channel 1, channel 2, and channel 3 of an EEG. What I observe here is actually a mixture of underlying sources. So imagine that in this brain at this moment there are 3 active sources. Might be an epileptic activity, some epileptic spikes. There might be some alpha oscillation in the occipital lobe, and there might be some background activity in a parietal lobe. Okay, and with EEG, all these activities propagate to the surface. They mix together, and that's the mixture that I'm recording. So what is the problem in blind source separation? In blind source separation, I'm only measuring the observations, and that's a matrix X. And I want to be able to reconstruct the time course of the underlying sources. And the mixture is determined by this matrix A. You can see it here. And each element of this matrix tells us, so for example, this element tells us how strong is the first source on the first observation channel. So if I change this mixing process, for example, like that you see I increase this number. So this tells us how strong is this second source on the third channel. So if I change that number, if I change that number, suddenly the epileptic spikes are very much covered in this background activity. And when does this happen? If for some reason that source becomes stronger, or if this source happens to be closer to the electrode, then it will have a larger weight. So in blind source separation, I want to estimate the sources, and I need to estimate these weights in the mixing matrix as well. And what do I want to achieve with this? For example, I want to, if I estimated them and I see that, okay, this source is not of interest because it's an alpha oscillation. I don't want to see the alpha oscillation. It disturbs my signals. I can just simply make the corresponding column of the mixing matrix all zeros, and I can reconstruct by multiplying A with X and then A with S, and then I will get a denoised version of the measurements. Another important way to use blind source separation or the mixing matrix and try and interpret these values here, because as I said, these values tell me how strong is a given source on the different channels. And this relative strength can tell me something about the location of the source. We will see this in a minute. So this I explained to you already. So if I have a matrix decomposition, a matrix factorization, so the estimation of A and S, it's not possible to do it in a unique way unless I add some additional constraints to this factorization. For example, in independent component analysis, people say, I want sources which are statistically independent from each other. And that will give you a single best solution. If there is no such constraint, then because of this formula that I'm showing you here, I can take any matrix M, which is invertible, and basically modify my sources, and it gives you apparently the same solution, numerically the same fit. But then I cannot interpret this, because which is my true mixing matrix, A or A hat? With tensors, I do not have the same problem. So how can I use tensors to demix the EEG observation? The general pipeline is the following. I have a matrix. I want to tensorize this matrix, for example, by expanding the observations in the frequency domain by short time Fourier transform or wavelet transform in this case. So each channel will be represented by a time frequency matrix. Then I select a tensor model, in this case a CPD, a rank 2 CPD. I compute the CPD, and then I can interpret these vectors. So these are the rank 1 constituents, or these are the columns of the factor matrices. And each of them correspond to characteristics of the data in one dimension. So for example, these vectors will describe the component along the frequencies. These vectors tell us something about the time course of the component, and this tells us something about the distribution over the channels. And of course, the most important thing to realize that each of these rank 1 matrices corresponds to one underlying source. Or at least that's the assumption that our underlying sources are rank 1. So the assumption, what does rank 1 mean in this case? The assumption is that each source has a certain time course, a certain fluctuation in activity, and this activity stays same along the frequency axis, and it also stays the same across the channels. That's why it's rank 1, because when I say it stays the same, it means that I'm just observing the exact same pattern, but with different weight. And the weight depends on how far is the actual source from my electrode. So now, once I computed the decomposition, I can then visualize the values along these vectors. So this is component 1, and this is component 2. Let's start with component 2. So this is the time course of my component. It has a certain frequency spectrum. It seems it has a peak at some low frequency. And if I project the channel values over the scalp, then I realize that there are very high values on these frontal channels, which are actually very close to the eye. So this component is nothing more than the patient is blinking or moving the eye. And then the other source, I see here the time course. You can see that it's a rather regular oscillation. It has a frequency of around 6 Hertz, and very large values here in the front on the left. And if I look at the original image, actually I see that, yeah, indeed there is this regular oscillation on the channels indicated by red. And after discussing this result with the neurologist indeed said, yes, this patient had an epileptic focus in the left frontotemporal lobe. So this scalp map nicely described or predicted where the focus of the epileptic seizure was. So to say a little bit, to tell you a few words about epilepsy and the research that I've been conducting in the last 10 years. So it's a neurological disorder, and a lot of approximately 30% of the epilepsy patients, they cannot be controlled by medication. And if they have focal epilepsy, which means that the seizures originate from a certain network in the brain, then you might choose for brain surgery, where you disconnect this network from the rest of the brain, or cut out this region. But for a successful surgery, you really need to precisely localize the seizure. So I've been working on different methods to help this. You can imagine that you would not do a surgery based on just one source of information. But the diagnosis is based on really a lot of different diagnostic tools, such as video EEG monitoring, interictal EEG fMRI. This is more like a research tool. You would look at structural, anatomical images, a PET scan, a Syscom, and so on and so on. But today I will show you some more examples of EEG analysis using tensors. And I will also show you, tell you something about EEG and fMRI integration to localize seizures. So here is another example of a seizure, or maybe it's even the same patient because it looks very similar. Basically, what you want to do is identify the channels where the seizure originates. In this case, it seems easy, but in other cases, it's very, very difficult because the pattern is not always so clear. So you want to automate the visual analysis and you might want to remove artifacts from the EEG. And well, I showed you the pipeline before. From an observation matrix, we want to construct a tensor such that we can do a unique decomposition. But which tensorization you choose, is it a time frequency transformation or something else? It really depends on what you think the underlying signals, source signals, look like. Because in seizures, we think that this is an oscillation, it makes sense to look into the frequency domain. But another way to look into the data is via Henkelization. Why? Because, well, Henkelization allows to represent the signals as sum of exponentials or sum of exponentially damped sinusoids. So if a signal is a combination of a few exponentials, then we know that the corresponding Henkel matrix is of low rank. And if we know that it's of low rank, then we must think of tensor decompositions, low rank tensor decompositions. Now, if you think that the underlying signals might look like some rational functions, then you might want to do linearization. But well, during this talk, I will stick to time frequency and Henkelization. And so, but it's very important to consider what kind of waveforms do I expect in my data. Accordingly, I have to choose my tensorization, and I have to think, okay, is it going to be then a rank 1 or a low rank method? In previous example, I showed you that the seizure in that case was rank 1. But if I do Henkelization, then it's actually low rank, because I said that the seizure is the combination of at least two exponentials, right? Because if I take an exponential and its complex conjugate, that will give me a sinusoid oscillation. So at least I'm dealing with rank 2 components. Well, maybe I can skip this slide. These are some practical considerations. If there is time, I will come back to it. But basically, let me show you how the Henkelization looks like. So this is a Henkel matrix. The Henkel matrix is nothing more than taking the values in the time series, so A1, A2, A3, all the way till AS. And I organize them in a matrix where each row of the matrix is a delayed version of the previous row. Okay, so let's say that the first row might be the values until here, so between 0 and 2. Then the second row is between, I don't know, the second sample here until the second sample after 2 seconds, and so on. So I take overlapping segments and I put them into a Henkel matrix. Now I know that it's from system identification theory. I know that these Henkel matrices must be low rank, depending on how many sinusoids I need to describe my underlying signal. So to decompose this tensor, a CPD, which is rank 1, will not be sufficient, but I need a decomposition which is slightly more complex, and that's a BTD. And in this case, it's a BTD with multilinear rank LL1. What does it mean? Now my components, I represented as low-rank matrices, low-rank tensors. And in this case, basically, so if I multiply this matrix and this matrix, that will give me a rank L matrix. So I assume that it's a rank L matrix with taken the outer product with a vector. And again, the low rank matrix will be the Henkel matrix of the underlying sources. But still, I have the assumption that the sources are the same, but scaled over the different channels. And this scaling, or the spatial distribution, will be given by this vector here. So what happens if I run my BTD model on this data? with rank equal to 2, then I get this very strange oscillation. So this is the multiplication of these two matrices. But I have a pretty nice spatial distribution. So it turns out that I can very well represent the data in space, but if I want to get more details about the underlying activity, then I have to increase my rank, because rank 2 was not sufficient. Well, why not? If I look at the first channel, for example, here, I can see that the seizure starts with a slow oscillation, right? But then later on, it speeds up. You can see perhaps here yourself that the signal here is of higher frequency. So for sure, I need at least 2, if not more, sinusoids to nicely represent this data. So what happened if I increased my rank to 6? Then this is the resulting extracted signal. And you can see now here that the signal starts with a slow oscillation. Then there is some attenuation. Also here, I don't see much activity. And then this oscillation speeds up. Okay? So the selection of a proper rank is very important. One last note about this part is that the spatial distribution can be also very interesting to use in seizure detection. So in focal epilepsy, the spatial distribution of a seizure is always the same for different seizures. So this is a very nice feature to use. Once I know the location or the spatial distribution of the seizure, I can expect that the next seizure will be the same. So I can train a classifier to recognize such a pattern, such a spatial pattern. Okay, and it will classify new incoming segments by basically comparing it to this. So if I want to read a little bit about seizure detection, I have one example in the references on this. Sorry, I need to drink some water. Okay. And in the last 15 minutes, I would like to talk a bit about another technique, interictal EEG fMRI. So as I said, sorry, let me go back for one more moment. The EEG has very good temporal resolution, but the spatial resolution is not so good. So I can only talk about in terms of channels where the activity comes from. fMRI has very good spatial resolution, so it makes sense to use both in conjunction. fMRI has a drawback that it has bad temporal resolution, so I still need the EEG to know where the events take place, and then based on the fMRI, I can know where they take place. So let's see how it works in practice. Traditionally, someone, neurologist, would look at the EEG recordings and would mark the occurrence of epileptic spikes. So there is a spike here and here. And then you can build a vector with zeros everywhere except once at the time when the epileptic spike occurs. Okay, so this is a binary vector. And I'm trying to build a model of the time course of the electrical activity. However, I told you fMRI has a bad spatial resolution, bad temporal resolution. Why? Because fMRI measures the signal which is related to the oxygen concentration in the brain. If a brain region is active, then it uses oxygen, so this concentration changes. And this change in concentration is what I see. But this change in concentration is really slow compared to EEG. So I need to use the so-called hemodynamic response function. This is supposedly the shape of the fMRI signal in response to a short transient neural event. So I would convolve this model time course with the hemodynamic response function. And this gives me a much better model time course. So I expect that in the fMRI signal, in those places, those voxels which are related to epileptic activity, they will have a time course similar to this. Now, what do I do then? I can do a regression analysis. So I try to find voxels which have a time course like this. Okay, and this is usually done in the general linear model. Yeah, and I can solve this in the least square sense. And so the beta values, each voxel will have a beta value. It will tell me a large beta value will be in those voxels which are related to the activity, because in those voxels the time course is explained well by this model. Okay, and so this is a pretty successful approach, and people showed it before that it really finds brain areas with high resolution which are responsible for the epileptic activity. But this study unfortunately fails in a lot of patients. So where it works, it's pretty good, but in a lot of cases it does not work because, for example, and I will tell you more about that, sometimes the activation which we find is very widespread. So it's not only the epileptic focus, but also some other areas look like significantly related to that model time course. So why do we observe this widespread activation was the question I was trying to answer. I will skip a few slides because I don't have time to talk about basically the other problem. So I'm just focusing on this problem of widespreadness. So I think my hypothesis was the following, that in fact, what we observe on the EEG, it's not just, I mean, it's a spike, but the spike might represent different activities in the brain. So if I zoom in, it's actually more than just a spike. What I have, there's a spike followed always by a slow wave. And it's been described before that they might represent different neural processes. The spike might be some onset type of activity, and the slow wave might be inhibition, so when the brain tries to stop a certain activity, or it might be propagation, when the activity already spread to another brain region. So the goal of my research here was to try and disentangle these two, so the onset and the spread of the activity using EEG fMRI. Because so what I assume that the spike, the onset, would correspond to a region where the seizures originate, so the epileptic focus, while the slow wave would correspond to a region which is remote compared to the focus. So how did I do this? I did this on a group of patients who each had temporal lobe epilepsy, which is where we expect that the focus of each patient comes from the same brain region. And I also assume that the spike corresponds to the focus and the slow wave corresponds to a remote region. Now, if you have a certain patient where the spike is very large, then we can also expect that the response, the values in this region, in the measurements, will be large. And vice versa, if you have a slow wave, which is, let's say, small, then we also expect the activation here to be small. Okay, so that's just what I explained. So if we have a large spike, then a large response here. If a small slow wave, then a small response here. Now let's take another patient. It might have a very small spike, then we expect small activation here, but a very large slow wave, then we expect a large activation here. So this is very similar to the EEG mixing process that I showed you in the very beginning. Remember, we had sources and the mixing matrix A, and depending on the weights, the source looked smaller or larger in a certain area. Now, this is the same thing, but in addition, I think that it's the same weights determine the strength of the observations in the EEG as in the fMRI. So in a way, this is again a factorization problem, but a joint factorization problem, because my observations, so x1 and so x of EEG and x of fMRI, we have two observations, but one set of mixing weights or mixing matrix. So how can I do this? Again, this is just what I explained. So I have observations separately. I also have separate sources for EEG, fMRI, but the same underlying mixing process. So how did I do this? I took an average interictal spike from a certain patient, and I took the fMRI image, which in this case vectorized, but in the future this can be done better. Then I took the same data from other patients, so I have an EEG tensor and an fMRI matrix. And I want to decompose this in a coupled way. So this I decompose using a CPD, so as a sum of rank 1 tensors, where this vector describes channel distribution, time distribution, and patient-by-patient variability. Then the set of, and then this matrix, again, it's a voxels time patient matrix. And I describe it as a sum of rank 1 matrices, where this describes voxels, and this the patient-by-patient variability. And so this, I assume that these are the same. So these are the columns of the A matrix. This is a mixing process. So this is called a coupled tensor matrix factorization. And as a result, I don't have here a result slide, but I basically managed to show that basically I managed to show indeed that my assumption was true, that so basically I managed to show that the spike corresponded to the epileptic focus. So when I looked at the results, I compared the time course here and the voxel distribution in the same component, because these are basically the same components. It turned out that the spike and the focus was in the same component. So this was a very nice result. Now, this is on a group of patients, and if you want to do this in an individual level, that's also possible, and that's the work of my PhD student. It's a rather complex study, so I won't go into detail, but the main idea here was that I want to make a coupled decomposition, but not by coupling the patient-by-patient variability, but coupling the time courses of the EEG and with the fMRI. But it's not so straightforward to couple those because of what I explained, that the fMRI has a slow response. So basically, I need to define a transformation from EEG to fMRI. And this transformation is nothing more than this hemodynamic response function. So the nice thing about this algorithm is that it will estimate the EEG sources, the fMRI sources, and it also estimates the hemodynamic response function, which connects the two together. Because, very important to note, that this hemodynamic response function might be different for different patients, as well it might be different in different brain regions. And well, my final example is a recent work of another PhD student of mine who is trying to look at this hemodynamic response function in functional ultrasound. So it's a new ultrasound technique which can measure the brain both with high temporal and spatial resolution. And it's a very important tool in neuroscience. So we are looking at the brain of mice, and we are trying to characterize the functional ultrasound signal. And one very important characteristic is really the hemodynamic response function. And here in this convoluted mixture problem, really the research question is, can we estimate both the source time courses and the hemodynamic response function just by looking at the functional ultrasound observations? And well, the problem leads to a block term decomposition, so a low rank tensor decomposition as well. But yeah, this is a little bit more advanced thing, so I didn't want to explain it in detail, just to tell you that this is also possible with tensors. And well, if you're interested, then I recommend this paper to you. So to summarize, I showed you how blind source separation can be important in neuroimaging. Important to remember is that CPD can solve the blind source separation without any additional constraints like independence, and it gives you a unique solution. But if you have more complex data, then you might need a block term decomposition. So remember the Henkel based method, where also the frequency of the seizure changed. Then I also showed you coupled models for EEG fMRI integration, so coupled matrix tensor factorization. And well, I didn't have time to say, but in these complex models, it's very important to define some constraints to bring in prior knowledge. So, and the general framework was to tensorize the data, select an appropriate model, which is basically select the rank, and then interpret the components. Yes, so here are many references. I will show you, I will share with you the link where you can find my presentation. I will just copy it here in the chat. So yes, those were my slides. I'm very happy to answer any questions you might have.
Yes, participants, do you have any questions?
Hello, good evening, madam.
Hello.
Hello, am I audible?
Yes.
Ma'am, in Shear analysis using tensor decomposition, actually you are taking the EEG signal and then you are going for time frequency representation using STFT.
Mm-hmm.
Then you are going for tensorization. After tensorization, you are doing CPD. So in a nutshell, purposefully you are increasing the dimension. That means EEG is actually a one-dimensional data. You are purposefully making it two-dimension using time frequency representation. Then higher dimension, you are reducing it to a lower dimension using tensor decomposition.
Mm-hmm.
Is it right, sir? Is it right, ma'am? Whether the interpretation is right or wrong?
Yes. I never thought about it this way, but it's true. So in this example, indeed, I'm increasing the dimension for two reasons. Because I think if I use tensors, then I can have a unique decomposition. But also, very importantly, because I know that the sources which I'm looking for will be distinguishable in the frequency domain. So this motivation is very important, and maybe I didn't stress it enough. That okay, maybe the EEG appears as a matrix, but the characteristics which are important in my application lie in the frequency domain, in a third domain. So I do need to go to the third dimension. Sometimes it's needed, sometimes it's not. Sometimes the data comes in a third dimension. Remember in this other application, I had channel, time, and patient data. So inherently, I had three-dimensional data. So it really depends on the application. But you're right about it. So basically, I increase the dimensionality. But then I break it down again to lower dimensional data. But this time by decoupling or unmixing the sources which were jointly observed. I hope this answers your question. But the observation you had is correct, yes.
Yes, any other questions? Yes, Sabiraj, do you have any other question? Do you have any question?
No, sir.
Sabiraj?
No, sir.
Okay. And I think someone raised. Yes, sir. Participants, do you have any question?
It means either my presentation was very clear or too difficult. I'm very happy, by the way,
No, okay. So let me ask to the participants, how was the presentation? If I have to say, then yeah, the presentation cannot be better than this.
Thank you.
Excellent,
really,
excellent
really good,
presentation,
but,
madam. Excellent. Really excellent presentation. Lot of
yes.
efforts. Thank you, madam. Thank you very much.
Thank you very
organizers for organizing such a wonderful session with a very good resource person. Thank you, sir.
I think I forgot to give you contact details on the slide, so I'm trying to. I will type my email address here. Just one moment. So if you have any questions later on, please feel free to contact me. This is my email address. Yes.
Yes, other participants, any feedback you want to give? Because today, today morning also I gave some of these slides were, I mean, same, but yeah. Personally, I say it presentation can never be better than this. It was really good, but yeah, other participants, if you want to give any feedback. So someone said it was a really good presentation, excellent session, excellent, okay.
Well, thank you very much for staying until the end. It was the very last presentation of the workshop, if I'm correct.
Yeah, so tomorrow is the last day. I mean, yeah, we are left with one more session.
Okay, good. Okay. Well, I'm very happy that I could be here. And yeah, I wish everyone a very nice day further. And yes, I hope that
Yeah, so
me and Siva motivate you to use tensors.
Madam, one
yeah,
question, ma'am, before the end.
Yes.
Madam, if we want to learn the basics of tensor, which kind of book, textbook like that, which one will you suggest me?
To be honest, there are no good textbooks for the basics, but you could start by reading, let me see. You could start by reading this very last paper. This is an overview paper of the use of tensors for machine learning and signal processing. So this summarizes the most basic concepts and also practical considerations. So I think it's a good way to start. Also, you might browse to tensorlab.net, it's a MATLAB-based toolbox for tensor decompositions. That it has demos, it has a nice documentation. Maybe if you start with the demos, that's nice. So that together with the paper I can recommend. Or if you think you are better to learn these things from the application point of view, then this is my overview article. on EEG, fMRI, and tensors. So yeah, this is where I would start. This and TensorLab.
Thank you, madam. Thank you.
You're welcome.
Yeah, so in TensorLab also you'll find the documentation. In TensorLab, not only you'll find the software, but also a clear documentation you will find there. Right, Boris?
Thank you, sir. Thank you, sir. Today morning you gave a wonderful talk, and since we could we could understand the fundamental, it is easy for us to go through madam's slide, and then we were able to understand because of the basic which you have provided in the morning. Thank you very much, sir.
Okay, yeah, thank you. Okay, yeah, got it. So it was really an interesting talk, and I'm sure that this will attract, may not be all, but some of the participants to work in tensor algebra for their research area. And yeah, on behalf of the organizing team, yeah, thank you for your yeah, thank you for finding time for us. And yeah, from your busy schedule, yeah, we are really lucky that we have you today with us.
Well, thank you very
Yeah,
much for the
thank you,
invitation,
buddy.
and it was my pleasure. Goodbye.
Yeah, so see you. Okay, bye.
Sir,
Yeah.
sir, there is a question. Is there any relation between matrix decomposition and tensor decomposition? So
Okay,
matrix
1 second.
decomposition is not unique. You have told in the morning matrix decomposition is not unique, whereas tensor decomposition is unique. Other than that, will there
Yeah.
be any?
I mean, other difference, right? Are you asking about differences?
One question, sir, in the chat box. Is there any relation? Actually, madam is asking about relation between matrix decomposition and tensor decomposition, sir. Will there be any relation,
Okay.
sir?
Relation. Yeah, I don't know from which perspective she's asking.